다쯤이란 주주 건유의 다시
Yes.
건유의 다시. Thank you very much.
Yes, yes.
So this is, I don't have any slide about the university. It may be not so interesting for the students. This is myself. I graduated mathematics in the master degree, purely mathematics in the differential geometry in the complex number, and very high dimensional space. It's 72 dimensional. It's not 3-dimensional, very high dimensional. Pure science, and I joined Toshiba, and I am the programmer up to 35 years old. So I haven't touched any oscilloscope and something. But I studied some semiconductor. During this time, up to 35, I'm developing the TCAD simulation inside Toshiba. And I go to Switzerland, the ETH. At that time, that is a kind of the center, world center of the TCAD simulation. Now it becomes the synopsis Centauras, the synopsis model. At that time, my professor was Professor Fichtner, that is the developing leader of the TCAD simulation. Now it is synopsis. And I got the doctorate degree in there, and also moved to the university and establish a center. So anyway, so that is very good message. If you have another specialty in the master degree, doctor degree, you can change. If you have the mind to the another direction. But I wait maybe around 10 years. But during this time I make a programming in the Fortran. But it's a very good time to study the basic physics of the semiconductor and also some mathematical way of thinking for the device design. So anyway, just a quick look at what is our activity. The first one is the diode power devices. We have 3 CDD machine for the layers, N-type, P-type, and also the I layer, non-dot layer, and also ALD, the atomic layer deposition. We bought newly the plasma-assisted ALD, and we have 2 inch clean room and 4 inch clean room, very local. We have second floor, in the first floor we have, ground floor we have 2 inch clean room, and at another campus, about 40 minutes from our campus, we have 4 inch clean room. And also we are doing the collaborative work with the venture company. And also that this is very interesting topic, that we developing our own very small current sensor because we have to check the current in the module under the bonding wire. This is 250 micron thick, and width is just 1.7 millimeter. And you can put this one under the bonding wire, and you can check every current of the chip, individual chips. And this is Infineon IGBT. If you measure, it is surprising. Completely different current is flowed in the parallel switches. And I showed them in the Leo Lawrence, the result. He came to my laboratory and I showed him, he just said, no response. So, and also we are doing the TCAD simulation because my background TCAD simulation, and also monitoring, condition monitoring. Though this is with the statistical, statistical approach and measurement circuit. Now we are developing our board, and we already developed and sent the company, 2 companies to using this board, monitoring board for their own inverters, and they send us the data, and we analyze the data and feedback to the company. This is a kind of business, the 2 companies, and also the silicon wafer technology with the Samco. Samco is located in the Kyushu Island. And what was that? This is the gate driving technology for the digital gate. And this is the staff and myself. and he's in charge of diamond, and also I'm collecting the money for diamond, and he's enjoying the diamond research. And he's a newcomer for the high-speed motor. He's from India, and he's for the gate driving. And we had 2 postdocs, but he go to Toshiba, and he go back to India with IGBT venture company. Already India, there is starting IGBT company, design company started. And also in the, this is our campus, and the other campus, there is a, say Abe, he's he's from, he's the power electronics, also Hasegawa sensei is and my super, his secretary, she's super, he's maybe most famous in this power electronics community sometimes. And this is not officially announced, but now we are preparing. And in the March, we will have some integrated power packaging conference in Kitakyushu. But this is not officially. Don't take pictures. Maybe in a couple of weeks, we will announce. But it's just past the IEEE meeting and accepted. So sorry for that. But anyway, we will plan to the next year of the spring. We will do that. So please join. And you could see is potential partner. Maybe I ask you some donation for the conference. Okay, then I will go to the another slide. So this is the slide I used in the PCI in Ichiro Shanghai. And I organized a session of the power chiplet package. That's the, the motivation. What is motivation? Because the power electronics is getting smaller and cost down, size and cost down weight, as Professor Lee pointed out, especially EVD or on-board charge. From here you can take picture, no problem. Okay, so then if you look at the high-performance computing area, the chiplet is one of the key technology to improve the performance and reduce the cost and reduce the power consumption. The different chip in the one substrate, and it works like one chip. And maybe this idea will come to the power electronics. And one PCB or one substrate, and you can make the several chips of the power electronics and gate driver and controller, and one PCB will be the power electronic system. So this now, I would say, power semiconductor guy and controller or gate driver and the substrate have to be designed together, not separately. So this is a motivation, and maybe this translation is done by the AI. I'm not sure it's correct or not, so, but maybe help. Okay. So, just I will present this part. And there is many companies like in the mainland China, Access, and from Japan, our electronics, and he is my friend in Toshiba. And also Fraunhofer in Germany, Schweitzer and AT&S, they are the very big activity. So that PCB technology, not actually PCB, but some plate technology is very important in the future. So the agenda is like this. So what is the chiplet in the high performance control? And also what is the roadmap for power semiconductor? And what will be the chiplet? And it's different level, and then conclude my talk. Okay, this is chiplet. Maybe you have the experience to look at the photograph of chiplet. And this is just I draw from the information from Intel. There is a compute. This is the CPU or GPU actually, and high bandwidth memory and I/O. And in total, this is one single GPU. Okay, but different chips, small chips, and in total, 50 chips together, small 50 chip together, and this becomes a one GPU. And this is because these chips are very low yield if you make the big chips, so they want to make the chips very small. And this is the kind of next generation strategy, but you need very good connection die to die. This is the Intel's EMIB, Embedded Multi-Die Interconnection Bridge. This is very important technology. So why it is needed? Because the computation power, what we need is here up to here, 2 times every year, but now 10 times every year. So it increased very, very rapidly. And if you look at the energy or power for the AI, this is from the DOE, the energy in the United States, the Department of Energy in the United States. Okay, look at that. This is forecasted, and they recalculated recently. Then, 2030, they need this big change. This is around 60 gigawatt. 1 gigawatt is one nuclear power plant. So 60 gigawatt. That is very, very huge change of the energy demand. So this means the energy issue will limit the performance of AI or development of AI. So energy issue is key for next generation technology with AI. That's a very important point. And another point, we have to minimize the transistor. This is the computation per kilo, 1 kilowatt hour, how much the calculation you can do. Every 1.75 year, it's twice. So from the very long time ago, now it's going to up and up. And this is 1,000 times. So this rapidly increase the computation performance. But for energy, we can reduce the energy for our computation, and then we can get a very high performance computing. And what we need is we have to reduce the transistor size and EUV and come to the 1 nanometer, 2 nanometer level. So without this, we cannot achieve the high performance computing. But the problem is yield. Yield is a problem. So this is the lithography of ASML. And this is the ASML, the twin scan. The cost, this is $100 million, 100 million US dollar. And 10 million, 100, and about 500 million US dollar for one single lithography patterning machine. It's very expensive, very expensive. And also, but become a very small size, then chip cost increase, but the yield, how much of the chip can be good in the wafer, the yield is decreasing very much. So this is the typical one. I make the calculation by the Excel. This is very easy calculation. You can do by yourself with the learning curve. And one monolithic to 4 chips. Then what happened? This is a week for development, and this each curve is the yield. This is monolithic solution. This one. This is the developing time. So yield is getting up and come to maybe 85% or something like that. But it takes years. But if you divide 1 chip to 4 chips, 8 times 4, then you can increase the yield about twice, and you can get 20 weeks ahead. This means that you can reduce the developing time. This technology is very, very competing, so this is big advantage of the developing time and also the yield. So the chiplet is very important technology for the future semiconductor devices in the high performance computing. So, but anyway, the small weight chip system and also the different process node is designed inside the single substrate. And this is very important to reduce the increase the computation performance and reducing the power consumption. And as I told you, that's the energy, nuclear power plant need 20 years to increase the, to build. But the AI is much faster. So we have to reduce the power consumption in the AI chips. So that is, chiplet is very important technology. So let's move on to the power. Okay, this is the power electronics roadmap. This is from the first announced by Ohashi-san. And it says every 15 years, the volume of the power electronic system is 1/10. So this is, it comes like that. This is from the report from Professor Takahashi from Tohoku University. They announced that they will achieve here next year. So this means that the roadmap becomes going like this, and 2035, 1 kilowatt, 1 cc. 1 cc is 1 cubic centimeter, just the size of chocolate, single chocolate. We converting the 1 kilowatt, that's very huge power density. In 10 years, maybe I will be already retired. So I can say anything because I don't have any responsibility. I will retire, but you are the student will become the real engineer in this. So you have to challenge the 1 kilowatt per square centimeter per cubic centimeter. Okay. And also the chip size will be decreased if the IGBT or essential IGBT, essential MOSFET, and coming to diamond for 1.2 kilovolt plus. The chip size, this circle is the chip size for the same performance or the similar performance, and this is the switching loss and also conduction loss, switching time. And if you apply the wider band gap, and this makes the high performance and also the smaller chip size. The smaller chip size in the power semiconductor, smaller chip size will be the important, will be coming. And also the trend of the cost of power electronics. So in 2022, I investigated by internet data or something, collecting the data, and found the PV inverter case. If you install twice, the cost is 20% down. It is very, very rapid decrease of the cost of power electronics. Doubling the cumulative production, it's roughly the market getting maybe twice, and the cost price is 20% down. This is very rapid reduction of the cost is required in the power electronic system. And also the PCB, maybe today's topic is the PCB. Then this is the 2010. The power electronics used on the PCB, the power limit is here. Okay, this is some commercially available inverter or some power supplies. This is the voltage and this is current. This is the line of the limit at that time, 10 years ago. Now, if you look 15 years, now PCB based power electronics 10 times higher than the before. This is quite coincident with the power electronics roadmap. PCB performance, the power electronics on PCB is getting higher power and higher power. It's 10 times in this 15 years. This is the Infineon case, and this is the FERIC converter. The volume is very small. Okay. And actually, this Infineon one used the chip is inside the PC. So this is already the power chiplet started. Okay. So now, yeah. Okay. Sorry. if you look at the yield in the power semiconductor, and I defined now new yield. This is, for example, chip yield means if you have defect, the chip size is 10 millimeter, 10 millimeter. There is a pink is defective, and the green is okay. But if you reduce the size of 5 millimeter, 5 millimeter, you have more good chip. But if you look at, there is an active area. So this is the dead area before the edge termination or gate wiring. But if the defect is even in this area, you have to, this chip is become the no good chip. And because of the guarding some termination structure. And I calculated, this is very simple calculation, you can do by X, so just I make the calculation by X. If the termination area is 200 micrometer, the most best chip, for example, if you reduce the defect density down and down, the optimum chip size changes like this. And if you go down the defect density, for example, here, the 10 millimeter is the best chip size to get the in terms of the active area yield. But in the silicon carbide or high wide gap device, this dead space and the termination area getting smaller and smaller. Then, for example, this one, the best chip size is different from silicon. It's a nonsense to make the big chip in the silicon carbide because the yield is getting worse. So the best chip size, for example, is 50 micrometer. This chip size is maybe 3 millimeter, 3 millimeter. This is the best chip size for each defect density. So the optimum chip size, according to the yield, the best chip size is different from silicon and silicon carbide or wider bandgap device. And also, if you use a smaller chip, this is the Toshiba presentation, that the smaller chip and separate, then you have the more thermal advantage in heat dissipation advantage. Then I try to calculate by the Excel, that's some analytical model. This is 6 millimeter chip, and this is the 9 of 2 millimeter chip. And the heat, the thermal resistance getting reduced like this. So if you have separate the chip to the smaller chip and separate, then you can get about half of the thermal resistance. This enhances the heat dissipation. You can use more higher power in the same chip area. So the gate drive circuit. So now we think, for example, 9 chips, 2 millimeter, 9 chips. How can we operate this one? And we have some experience. This is a case we developed in Toshiba and 42 chips in parallel in the pressure contact package. And experiment, there is a big oscillation inside the package. But we designed very well designed PCB wiring inside the package. This diameter is more than 10 centimeters, about 12 centimeters. Actually, this post size from here to here, 125 millimeters. And there is 42 chips in parallel. But if you have the good optimized PCB wiring, no oscillation. So in this sense, maybe the separated smaller chip, we need a very good wire inside. And if you put these chips inside the PCB and wire the gate to the very precise design, then you can make the very stable operation of the chips. And also, we have to reduce the parasitic inductances. This is the performance of the lateral devices, silicon to diamond. And this is the R1 QSS. This is the kind of the speed benchmark. And if the diamond or GAO or gallium nitride, it has a maybe 2-digit to 3-digit higher switching speed. We have to be carefully design the circuit, otherwise it makes the noises very easy. Okay, and system level. If you know that to look at the high power module, that is very strange point. One outside, the one kilovolt, for example, outside you need 1 centimeter to isolate. But inside, just 1 millimeter is sufficient. So outside in the air, you need the clearance and clipping to keep the reliability for the discharge. But inside the package, only 1 millimeter is sufficient. So this means, and this is about the 1 kilovolt, maybe 0.51 to 1 centimeter for the this is the elevation. So it's better to make everything small, put everything inside, not outside. Put inside. That is very important. So and system integration. This is the example of the bidirectional gun from Infineon, for example. There is a very complicated system, and 2 gate driver and 2 DC-DC converter for the gate driving. And also you need the terminal for the substrate biasing circuit. And source 1, source 2, this is bidirectional conduction to this direction. Okay, then. And the red lines isolation, we need 1, 2, 3, 4 isolation areas for the bidirectional gun device. Maybe another, even the silicon device, you need 1, 2, 3, 4 isolation. And now the Infineon provided this part. And the other part, they are asking that the user have to do. But I think we have to, the semiconductor company have to do everything, also including the isolation inside the PCB. Then the user can use this system as a one single chip, like a chiplet in the GPU. This system can be, well, if you make everything inside the PCB, this can be very easy for user to use, and with very high performance. Okay, so then this is almost a conclusion. Now there is a 4-layer level of the integration. Maybe I have made it translated. Okay. So this is just the package as with the PCB, the existing product. This is the level 2 is the chip in the current version with the chiplet philosophy. So make the system with the existing chip. And the 3rd layer, the chiplet with the special designed chip for the chiplet, power chiplet. And finally, it's the chip and the PCB co-design. So the chip design have to be changed. For example, you imagine that one single chip has 1 gate pad. But if you use PCB, the gate pad can be maybe, for example, 5 gate pad on the chip and connect on the PCB, in the PCB. It's possible. So maybe optimum design, the electrode can be separated and connected by the upper layer, meaning the PCB layer, and the tip coupler, and reduce the inductance and reduce the resistance. So I think that the final goal is this one. Design the semiconductor chip and package, I mean the PCB, co-design, optimize the chip, considering the PCB and PCB design considering the chip, and optimize the size. That's kind of the loop of the optimization. This is the final stage of the power chiplet. But there is a many problem. This is the problem. So, still very high cost and reliability, standard. Standard is very big issue. Now TSMC doing in the chiplet, in the high performance computing GPU, 3D blocks. This is very good start of the TSMC. But there is many problems. So that's it. And I will retire in a couple of years. So this is the homework for you. Okay, thank you very much.